Somewhere in the darkness, 13.5 billion light-years away, something is burning. Not a star, not a nebula, a galaxy. Blazing impossibly bright, impossibly early in the life of our universe. And it should not exist. Not yet. Not then. Its name is MOMSI 14, and the scientists who found it called it exactly what it is: a cosmic miracle. Light is the fastest thing in existence, 186,000 miles per second. Nothing beats it. Nothing comes close. And yet, even at that speed, crossing the universe takes time. A staggering, incomprehensible amount of time. So here's the trick astronomers use. They don't travel to the past. They don't need to, because light carries the past to us. When you look at the sun, you're seeing it as it was 8 minutes ago. When you look at the nearest star, Alpha Centauri, you're seeing it 4 years ago. The Andromeda Galaxy? You're looking 2.5 million years back in time. But JWST doesn't stop there. It was built to see something far more ancient. It was built to see the first light that ever crossed a transparent universe, to witness what astronomers call the cosmic dawn. In the beginning, the universe was not dark. It was blindingly hot, a plasma of energy and matter so dense that light couldn't even move through it. Then, about 380,000 years after the Big Bang, things cooled enough for hydrogen atoms to form. And the universe went dark. Astronomers call this the cosmic dark ages. For hundreds of millions of years, there was nothing to see, just a cold, dark ocean of hydrogen and helium. No stars, no light, nothing. Then, slowly, gravity did its work. Gas clouds collapsed under their own weight. Temperatures inside rose to tens of millions of degrees. Nuclear fusion ignited. The first stars were born. And those first stars were monsters. We're talking hundreds of times the mass of our sun, burning so hot and so fast that they lived only a few million years before detonating as supernovae. But in their short, violent lives, they did something critical. Their ultraviolet radiation began blasting apart the neutral hydrogen that filled the universe. This process is called reionization. And when it was complete, the universe became transparent for the first time. The cosmic dark ages were over. That moment is what JWST was built to observe, and now it has pushed deeper into that era than any instrument in human history. Welcome to Cosmic Chronicles. We have noticed that 91% of you that watch this channel frequently do not subscribe. If you've ever enjoyed my video, please could you do me a favor and hit the subscribe button? It helps this channel more than you know, and the bigger the channel gets, the more valuable content you enjoy. In 2025, a team of astronomers at MIT's Kavli Institute was combing through existing JWST image archives, looking for anomalies, looking for objects that didn't quite fit. And they found one. A faint object appearing in infrared wavelengths, but vanishing completely at shorter wavelengths. That vanishing act is actually a signature. It's called the Lyman break technique. When light from a distant galaxy travels toward us through the expanding universe, it gets stretched, redshifted. The farther the galaxy, the more stretched the light. At extreme distances, everything below a certain wavelength gets absorbed by neutral hydrogen along the way. The object simply disappears below a cutoff point, like a star that only shows up in night vision. This object had that signature, and it looked very, very far away. So, in April 2025, the team pointed JWST's NIR SPEC spectrograph directly at it. They split its light into component wavelengths, measured 5 distinct emission lines, and confirmed what they suspected. Its redshift Z equals 14.44. This galaxy's light left it when the universe was just 280 million years old. That makes it the most distant object humanity has ever confirmed, by any measurement, in the history of science. They named it MOMSI 14 from the Mirage or Miracle survey that produced it. The researchers called it a cosmic miracle. After peer review, published in January 2026 in the Open Journal of Astrophysics, the title held. The universe is 13.8 billion years old. Now, if you compress that entire history into a single calendar year, this is what it looks like. January 1st, the Big Bang. January 7th, MOM-Z14 exists, the galaxy we just found. Late January, the Milky Way begins to form. September, our solar system is born. December 25th, dinosaurs appear. December 31st, 11:59 p.m., modern humans arrive. And right now, in the last few seconds of December 31st, we built a telescope that looked back to January 7th. That's what jwst just did. MOM-Z14 sits 33.8 billion light-years from Earth right now in proper distance, because the universe has expanded since that light left. Its light traveled 13.5 billion years to reach us, and it arrived on a golden mirror 6.5 meters wide, floating 1 million miles from Earth. MOM-Z14 is tiny, just 241 light-years across. The Milky Way is 100,000 light-years wide, so we're talking about a galaxy roughly 400 times smaller. Its mass is about 100 million solar masses, comparable to the small Magellanic Cloud, a dwarf satellite of our own galaxy. By every measure of its size and mass, it should be dim. It is not. MOM-Z14 has an absolute UV magnitude of -20.2. For context, pre-jwst models predicted galaxies at this era should be 100 times less common at this brightness level. This galaxy is blazing more than 100 times brighter than our models predicted anything should be at this distance. And it's not alone. The researchers estimate that the number density of bright galaxies at this redshift range is more than 100 times greater than pre-jwst consensus models predicted. More than 100 times. Not a rounding error. That's not a minor adjustment to our models. That's the models being fundamentally wrong about something. But what? When astronomers analyzed MOM-Z14's spectrum in detail, they found something no one expected. A chemical signature. Nitrogen. Lots of it. Relative to carbon, far more than we see in normal star-forming regions. This kind of elevated nitrogen-to-carbon ratio is not common in the general universe. But there's one place where we see it regularly. Globular clusters. Globular clusters are some of the oldest structures in our galaxy. Dense, tightly bound spheres of hundreds of thousands to millions of stars. They show this exact elevated nitrogen pattern, what researchers call a second population chemical signature, because they formed in extreme environments. Crowded, compressed stellar nurseries where supermassive stars ran into each other, merged, and produced unusual nucleosynthesis. We've always assumed globular clusters formed in the first few billion years of the universe. But MOM-Z14 has this signature at just 280 million years post-Big Bang, which means globular cluster-like environments, the most ancient stellar structures we know, may have begun forming almost immediately, not billions of years after the Big Bang, within the first cosmic breath. The researchers write, and I quote their conclusion, "We may be directly witnessing the formation of such stars in dense clusters, connecting galaxy evolution across the entire sweep of cosmic time." That's not a minor footnote. That's a rewrite of billions of years of assumed stellar archaeology. So what's actually powering MOM-Z14? Here's what the data tells us. Most of the light from this galaxy comes from stars, not from an active galactic nucleus, not a black hole engine. Stars. But not ordinary stars. The chemical signatures and extreme luminosity suggest the presence of supermassive stars. We're talking about theoretical objects that can reach 10,000 to 100,000 times the mass of our Sun. Stars so extreme that for most of modern astronomy, they were considered theoretical curiosities. The primordial gas of the early universe, almost pure hydrogen and helium, couldn't cool efficiently the way modern gas clouds can. When it collapsed, it didn't fragment into many small stars. it collapsed directly into massive, dense stellar structures. Objects that could produce exactly the kind of nitrogen enrichment we're seeing in MOM Z14. Harvard astrophysicist Avi Loeb, who has written about MOM Z14 in depth, notes that the nitrogen spectral features observed cannot be produced by normal stellar evolution within 280 million years. The physics simply doesn't allow it. Something more exotic had to have been there first. Something forged in the very specific conditions of a universe that had only just switched the lights on. Now here's what separates this discovery from interesting anomaly to fundamental crisis in cosmology. MOM Z14 is not the only one. Since JWST began science operations in July 2022, it has found galaxy after galaxy that is too bright, too massive, too chemically evolved for the moment we're seeing it at. GNZ11 at redshift 10.6, JADES GSZ140 at redshift 14.18, MOM Z14 at 14.44, and dozens of others between them. The number density of bright sources at these early epochs is more than 100 times higher than our pre-JWST models predicted. Our cosmological standard model, called Lambda CDM, has been extraordinarily successful. It explains the large-scale structure of the universe, the cosmic microwave background, the distribution of dark matter, but it keeps failing in the early universe. Some researchers are proposing that early dark energy, a brief burst of exotic energy in the universe's first moments, accelerated early structure formation beyond what standard models predict. Others point to a top-heavy initial mass function, the idea that the early universe preferentially made massive stars rather than small ones. Others suggest that feedback mechanisms, like supernovae and radiation, operated differently in the early universe, allowing star formation to be far more efficient. One paper in Nature Scientific Reports raised the possibility that some of the extreme brightness could have a non-stellar source entirely, light production mechanisms we haven't modeled yet. None of these explanations is confirmed. All of them require revising something we thought we understood, and the data keeps arriving. There's a deeper implication buried in all of this that doesn't get talked about enough. The first stars in the universe are called population 3 stars. We've never directly observed one. They're theorized to be massive, hot, and short-lived. Born from pure hydrogen and helium, with none of the heavier elements we call metals in astronomy. They lived fast and died violently, seeding the universe with the first carbon, oxygen, nitrogen, iron, the elements everything else is built from. According to our models, population 3 stars should have appeared somewhere between 100 and 400 million years after the Big Bang. MOM Z14 sits at 280 million years, and it already has heavy element chemistry. That means population 3 stars lived and died. Multiple stellar generations may have already cycled through before MOM Z14 existed. Which means the very first generation of stars may have appeared much earlier and burned out much faster than our models currently predict. JWST's researchers said it themselves. The telescope is pushing toward redshifts where we might, for the first time in history, directly observe a population 3 star. The very first light the universe ever made. MOM Z14 holds the record right now, the farthest confirmed galaxy in human history. But it won't hold it forever, and the researchers know it. The Mirage or Miracle survey that found MOM Z14 covered only about 350 square arc-minutes of sky. The full observable sky is about 148 million square arc-minutes. We've mapped a fraction of what JWST can reach. And already the universe is defying every expectation. NASA's Nancy Grace Roman Space Telescope, launching in the coming years, will survey enormous swaths of sky with JWST-level infrared sensitivity. It will find hundreds, possibly thousands, of galaxy candidates like MOM Z14, each one a timestamp, a photograph from the universe's first chapter. Every photon that lands on these mirrors carries information encoded 13 billion years ago. Every spectrum we decode is a message in a bottle from a universe that didn't even have planets yet, and we are only just learning how to read them. Here's what I want you to carry with you. Every single dot of light in a jwst deep field image is a galaxy. Not a star, a galaxy, containing hundreds of billions of stars. And in that field, we found one, a single red dot that existed when the universe was just 2% of its current age. That galaxy burned for hundreds of millions of years and faded. Its stars lived and died before Earth even existed, before our sun was a thought. And its light, ancient, stretched, reddened by 13.5 billion years of travel, arrived at a mirror we built, above an atmosphere we evolved under, on a planet around a star that hadn't formed yet when that light first began its journey. That's not just astronomy. That's the universe looking at itself, through us. Thank you for watching, and see you in our next video.